So this is a mesh again. It's your example. You can see. We'll put it in opacity. You can see all the detail. I think this is Martin Bishop's heart. Make it a bit. You can do the culling, and you can see blood vessels, and etc. in it. Again, if you have a really big mesh and you move it and it's transparent, it has to do calculations because to properly draw it, render it in 3D, you have to sort all the elements from near to far. So that's why you see there's a pause afterwards sometimes while it recalculates it. So it, but it looks, so it's pretty competent, good. Go back to the fill color, go back to the opacity. So here is one of the examples of what you can do. So there, by changing the like made it gold. And you can see that, how did we change? If you look at the lighting, very low ambient light. So there's the ambient light, so very low with the ambient light. High on the specular light, pretty high, very high on the specular. And if you go look at the surface, we can see we have a low value for shiny. So shiny means, like, this is like a spotlight. You can see that the shine is more concentrated the higher the number is. So metals are more like here. And then specular is just the intensity of that light. Shiny is how much that light spreads. And then diffuse is based on the angle of incidence, how bright that particular is. So you can get some pretty nice effects. Here's another nice effect. I don't know how I did this. I just found it one day. So really, again, you have the tools. You have that you can get some pretty nice effects on some pretty good looking hearts, which is one of the main purposes I want for this piece of software. And if you want, so here's clipping to show you what the performance is in clipping. And if I look at I'll tell you how big that mesh was. So that was how many volume elements? So that was 24 million volume elements. So that's not too bad. Okay. Okay. It can also do vector data. So this is an example from a paper we just did, looking at an electrode, looking at connections in here. Might even have connections. So this is a block of tissue. Here. Surfaces. There's bath myocardium. So let's visible. And so there we see this is an electrode. Well, that's the shaft of the electrode. That's the ring. That's the shaft. And if I get rid of this, you can see the tip. And this is the electric field produced in the tissue. Again, you get the dog bone pattern. And if we want, you can see what we also imaged the current flow. So this is when the electrode is on. We can see there's those are isopotential lines. So that's sort of a zero isopotential line going around the box. And you can see there's the shaft of the electrode. So the color is the transmembrane voltage. sorry, no, sorry, the color is the extracellular potential. And you can see the current flow. So those are, and we can actually make this bigger. See, so you get really intense. You can see you have really big arrows. And so with the arrows, you have lots for the vector data. You can have the color of each arrow dependent on the magnitude of the vector, or you can just do a fixed color. If you might want them all red, if you want them all blue. Again, likewise, you can have the length of each vector depend on the vector magnitude or on a fixed value. You can also add a fourth field. So for each point of vector point, you can have the vector, but you can also have an additional fourth, just a scalar associated with it. And then you can use the length of the vector to also depend on the scalar, or the color depend on the scalar, but I didn't have the scalar data available. And again, I think I have, so I can turn off the ISO lines if I want. You can, yeah, these are stochastic. So if I don't do it stochastically, what happens is when you sample, so I have, there's many more, you find with vector data, if you get too much vector data, it tends to cloud. So then there's a stride. So then that's, I'm actually only outputting every 20th vector. But you'll notice that when you do that, you get a regular pattern. You get, because you're sampling, so you get a multiple, and you get, you know, so it doesn't look as distributed. So if you do stochastic, so it's randomly picking every 20th vector, then you get a much better looking distribution. And then you can control the maximum length of, and then you can finally control how the vector is the maximum length, or for the colors, the minimum, like the typical color scale that we've been using. So let's just change the color scale. Offset the vector. There. Okay. So. Okay, so so those are vector data.